Hi everyone, and welcome back to Physics 11. So in today's video, we're going to be looking at tension. Now, this is an application of Newton's law. So it is found in the textbook in chapter 4, section 4.5. But again, the textbook goes into two-dimensional application of it. So it will be something you will see in grade 12 physics, but it has only, I think, one example with one dimension. So for Physics 11, you're going to be sticking to 1D tension questions. So let's take a look what tension is. So tension occurs within a material that is being pulled or stretched. So it's an internal force that acts at all points along a rope or a string or a chain in both directions. So if you're pulling, there's going to be equal and opposite force in the opposite direction of the pull. So here's an example, and this is probably one of the most common examples when you start looking at tension. So we have two masses, two cards attached by a rope being pulled along the flat surface. Notice in this case, we're going to neglect the friction. So in some other cases, you might have to also consider friction forces. In this case, we're just going to keep it simple. So we have two cards, and we have different masses. M2 is 6 kilograms, M1 is 4 kilograms, and they're being pulled by a force of 40 newtons. So part A says find the acceleration of the cards. In part B, find the tension in the string connecting them. So again, friction is negligible here, so we're not going to consider it. But in other questions in your practice package or in practice notes, you will see that some of the questions will have friction in them. So make sure you read the question carefully. Okay, so the first thing you want to do is come up with a free body diagram. Now in this case, I'm using the cards as the masses, so you don't have to do the whole card. You just draw a little square to represent the mass, and that's all you need for the free body diagram. Now in this case, if you have more than one mass, we have what's known as the F net for the system. So the sum of forces acting on all the masses together, we call that the system equation. We're also going to have the mass of the system, which is basically the sum of all the masses. So in this case, let's indicate all the forces. And if you have, again, more than one mass, you want to use some subscripts to distinguish between, for example, different normal forces, different forces of gravity. So in this case, we're going to have our M2. So let's draw the forces. So again, we're going to have our F normal, and this is going to be 2 because the M2. Down, we're going to have our Fg, and again, because of the M2, I'm going to write Fg2. On the other card, we're going to have our normal as well, because again, these are on a flat surface, but this is my Fn1, and this is my Fg1. Okay, now these are being pulled by a force of 40 newtons, so this is the applied force. Let's draw it up here. Right? And there's one more thing. Since we don't have friction, we don't need to include it, but we do have tension. So in this string, in between them, if the force is to the right, that means that we're going to have a tension force acting on the first card, M1, to the left, and on the second card, M2, it's going to be in the same direction as the force applied. So these are going to be our Ft or just T for tension. Now notice here that the two tension forces actually going to be the same in magnitude, opposite directions. So they will cancel each other out. So when you write the F net for the system, these two forces along the x direction here will cancel each other out. Okay, so that's one note to consider, to remember. So let's make this positive to the right. So my Fa is going to be positive here, the force applied. And let's write the tension, the F net for the system. So you're going to write the F net, and you can also include a subscript so you remember which one this is. This is the system F net, so we're going to write all the forces from all the masses starting from, let's say, the force applied. So I'm going to go from right to left in this case. So the force applied is positive, so I'm going to write F applied. Then I have tension, which is in negative direction here. Tension in the positive direction. And then we're going to have our mass of the system, or the total mass. So mt for total, times the acceleration. And this is in the x direction, where you can write system. Because we're working in one dimension, I guess you don't really need to distinguish between the x and the y. But if you have two dimensions, then you definitely want to include the subscript x to distinguish between different dimensions. Okay, so like I said, because the tension forces are going to be equal here, these two will add to 0. So they go away. So that means that our F net for the system is just going to be the force applied equal to the total mass times the acceleration. So again, our force applied equals to the total mass, so mt, times the acceleration. Now we do know the mass of each cart, and we do know the force applied. So we can find the acceleration of the system by just rearranging this for A. So A is going to equal the force applied divided by the total mass. So normally whenever you end up with a question that's asking you for the acceleration of the system, your total mass is always going to be in the bottom. So you're always going to have all your masses adding up at the bottom. So that's a very common way to check whether you're doing your calculations correctly. So let's plug in the numbers. So our force applied is was 40 newtons, 40.0. And our total mass is going to be 6 plus 4 kilograms. So you're going to do 6.0 plus 4.0. So again, we need to add the 6.0 to 4.0, which is going to increase the number of sig figs in the bottom. So right now we have 2 sig figs, but remember for addition, we count the least number of decimals. So we're going to end up with 10.0, and now we end up with 3 sig figs on the bottom. So it's going to be 3 sig figs over 3 sig figs. So the final answer should have 3 sig figs as well, which means this is going to equal to 4.00 meters per second squared. So this is the acceleration of this system, which means in this case each object is going to accelerate at the same acceleration of 4 meters per second squared. All right, so that's our part A to the question. We found the acceleration of the carts. Let's take a look at part B, which asks us to find the tension in the string connecting them. Now, since we said that the tension cancels out in the F net equation, we can just take one of the masses and do a separate free body diagram for each mass and find the all the forces acting on one mass. And again, we can use either one to find the tension in this case because we know that it will cancel out. So again, tension acts on both masses equally, so we can use either M1 or M2 to find the tension in the string. So first, let's draw the forces acting on each mass separately now. So again, we will have our normal force. So this is our Fn2, Fg2, tension, normal force, and force of gravity. And here we have the FA, F applied. But again, now we're considering each mass separately. So for example, if we want to find the acceleration using the first mass, or in this case M2, the one on the left, we can come up with the system of equations for system, the F-net equation for the M2. So for M2, our F-net in the x direction is going to equal to the tension. Let's make this positive. Okay. And the mass 2 times the acceleration. Again, the acceleration here is the same because we're dealing with one dimension. The x here is kind of not mandatory, but it's a good habit to get you used to labeling your accelerations because, like I said, in physics 12, you're going to be dealing with 2 dimensions all the time. So you had to be able to distinguish between your x and y coordinates. So the next step is then find the tension. Well, in this case, we know what the acceleration is already. We know what the mass is. All we had to do is just plug in the numbers to find the tension. So in this case, all we got to do is replace our M2 and the acceleration value with, let's see, we have 6.0 and the acceleration was 4.00, which leaves us with, again, 2 sig figs, 3 sig figs. Multiplication means least number of sig figs. End up with 24 newtons and 2 sig figs in the answer. So let's see if we can do the same thing with M1. See if we can find the tension from M1, even though we have more forces when we talk about the M1. So our F-net for this one is going to be tension is in the negative direction, our FA is in the positive direction, and this is going to equal to the M1 times the acceleration. So again, the goal is to get the same tension force of 24 newtons. So let's plug in the values, or first let's actually solve this for tension because we know what FA is. This is given, we found A. So the only unknown is tension. So let's rearrange this for tension, which in this case just moving the T to the right and moving the M1 times A to the left. So we're left with this, FA minus M1A equal to T. Okay, so let me write the T on the left side and plug in the FA value, which was 40.0, minus M1, which is 4.0, times the acceleration of 4.00 meters per second squared, and that's going to leave us with 40 minus 16. So again, we have 2 sig figs, 3 sig figs, so the multiplication gives us 2 sig figs, and then when you subtract, it's going to be least number of decimals. So 40 minus 16 is 24. So as you can see, we get the same tension no matter which mass you use once you break it apart and you have separate free body diagrams.